right, so we had started by reviewing our hydration of alkenes, so those top 3 reactions there from the first semester, but then we had introduced these oxidation of alcohols. I kind of gave away the punchline here, these reaction categories. I'm going to give you a reagent bank here, and you're going to pick which one you need in order to do each of these 2 transformations here.
I know, I'm waiting for my canvas to load too.
Let me know if it persists.
Is your canvas just not loading? No, on my phone. Yeah, same.
All right, well, I'll open it back up if it doesn't work.
I have to connect to the school board.
Yeah, I tried.
This is the most non-quiz of all the daily quizzes. It's literally just a survey, so I'm happy to open it back up at the end if we need to here.
This one is good.
All right, we're gonna start in on this alkene hydration business. I have this carbon-carbon double bond. I'm gonna color one of those carbons red and one of those carbons green. These hydration reactions, we're gonna add water to this double bond, meaning hydrogen on one side, the hydroxyl group on the other side. So let's start with this oxymercuration reaction here. Let me shrink this down so I got a little bit more room. All right, oxymercuration. Where am I going to put my hydroxyl group? On the red carbon or the green carbon? The red carbon. Why the red carbon? More substituted. So these are one of those Markovnikov reactions. All right, my regioselectivity, more substituted carbon. All right. What about these hydroboronation reactions? BH3. Now where's my hydroxyl group going to go? The red carbon or the green carbon? The green, the less substituted carbon, are anti-Markovnikov reactions. All right, and then lastly, our acid-catalyzed hydration reaction. Nothing fancy here, just dilute sulfuric acid. Now my hydroxyl group is going to go on the red carbon or the green carbon?
Neither.
All right, trick question. All right, which carbon is it going to go on? That tertiary carbon there, my more substituted, because these reactions here we had to watch out for those hydride shifts, right? These were our carbocation intermediates. We said we had to watch out for any shifts. Cool? All right, these were our ways to prepare our alcohols, starting with alkenes. Again, just a review, actually not even chapter 17 review all the way back from first semester. Okay, and then we introduced these new category of reactions here, our oxidation-reduction reactions. And so you're supposed to pick from this reagent bank here and tell me what you're going to need to use to perform each one of these each one of these conversions here. Take a second, fill it out, and then we'll go. All right, so first of all of these, both of these rather, reactions here would be examples of what? Oxidation or reduction? Oxidation. And how do we know it's oxidation? Because our products have more what? More oxygen, more carbon-oxygen bonds, right? So oxidation, we're replacing those carbon-hydrogen bonds with carbon-oxygen bonds, all right? The difference here is our primary alcohol is either being fully oxidized to that carboxylic acid, right? I'm converting this carbon-oxygen single bond into now I got 3 carbon-oxygen bonds, or I'm just oxidizing it that one step to that aldehyde here, all right? So we had these different reagents that we would use. Importantly, if we're going to fully oxidize that carbon, this is what we lumped into that bucket of our strong oxidizers. And if instead we're going to stop at that aldehyde step, this is what we lumped into that bucket we called our weak oxidizers. All right, so I got 4 reagents up here. Importantly, only 2 of them are oxidation agents. Which one's our strong oxidation agent? Yeah, the one that we saw in our previous chapter was oxidizing that benzylic position as well. This is my strong oxidizer. What was the weak oxidizer? Those acronyms, we had PCC and DMP. All right, that's our weak oxidizer here. Okay, so that's going the oxidation direction. That takes care of these 2. Importantly, these other 2, the lithium aluminum hydride and the sodium borohydride, those were examples of reducing agents, all right? And so when I'm talking about reduction, that means I'm going in the other direction here. Whoops, grabbed too much. Make a little bit more room. All right, so reduction means we're going in this direction now, reducing our aldehyde to a primary alcohol or reducing that carboxylic acid to a primary alcohol. All right, and how do I know it's reduction? Because now I'm replacing those carbon-oxygen bonds with carbon-hydrogen bonds. All right, so if we want to go the other direction, again, importantly, these reducing agents, we lumped into these same buckets of being strong and being weak. Does anybody remember which one was the strong one? Lithium aluminum hydride or sodium borohydride? The lithium aluminum hydride is able to reduce that carboxylic acid. You could, to be fair, you could use either for your aldehyde, but we could also use instead that weak reducer, the sodium borohydride. Either of those two would work for this. All right, and for our reduction reactions, we actually introduced our mechanism for these reactions. So importantly, the lithium, the sodium, right, those group 1 metals, they're just counterions. They're not doing anything in the reaction. The hydrides are the special part. So we took a look at our hydride Lewis structures here, and importantly, we said that when you hear this hydride, you're thinking that we have this nucleophilic hydrogen. And I know, everybody's mind was blown. You were like, what? Hydrogen's a nucleophile? Yeah, hydrogen's never a nucleophile, right? But in this case here, with these hydrides, that's the special role that these are playing, is our hydrogen in this compound is going to be playing the role of the nucleophile. All right, and if I told you hydrogen here was our nucleophile, that of course means that this is our electrophile, but where's our electrophilic site in this ketone? Carbonyl carbon, awesome. So, carbonyl carbon. All right, so our nucleophile attacks our electrophile here. Carbonyl carbons can accept pairs of electrons because they're going to bump that pi bond up onto that oxygen. What rule did I break here in my electron pushing arrows? Something's wrong here. Awesome. All right, so my hydrogen's my nucleophile. I can't start my base of my arrow at that atom. I have to put the base of my arrow at a pair of electrons. That pair of electrons there would be doing my attacking in this scenario. Okay, since that oxygen this is our mechanism that we looked at last time, so just to go quick here. Since this oxygen's accepted this pair of electrons, it's got this negative charge. There's always this follow-up step, we call this acidic workup, where we're going to add some sort of a dilute acid here, and the whole purpose is just simply to protonate that oxygen, creating our alcohol. Okay? Now, there's this very tricky way that the ACS loves to do to make sure that you're paying attention to the mechanism when you're doing your reaction. So first of all, like we said, this is our nucleophilic hydrogen. It's what did the attacking and is now bonded to that electrophilic, what was formerly my carbonyl carbon. Okay? Importantly, the acidic workup is where we protonated that oxygen there. So one thing that the ACS loves to do is a problem like this, where I'm going to give you this exact reaction. I'm just going to ask you what the product is, but I'm going to give you this deuterated reagent here, right? Remember, the D stands for deuterium. What is deuterium? What element is that? It's just hydrogen, but what's special about it is it's this hydrogen isotope that has a mass number of 2, right? Most hydrogens out there just have 1 proton. Deuterium has a proton and a neutron, all right? And they can use this to figure out where that specific hydrogen is going to go in your product. So everybody's going to take a second. They're going to give me the product of this reaction here, but they're going to tell me where that deuterium atom ended up in that product. All right, in this reaction, I'm forming 2 new something hydrogen bonds, right? I'm forming a new oxygen hydrogen bond and I'm forming a new carbon hydrogen bond, right? So my question was, where is that deuterium atom going to go? Is it going to go on the carbon or is it going to go on the oxygen? All right, so let's take a poll here. Who thinks it should be the top structure? Raise your hand. Okay, who thinks it should be the bottom structure? Raise your hand. Okay, importantly, if the deuterium is on my aluminum hydride here, that's my nucleophile attacking that electrophilic carbonyl carbon. That's the one that's going to be bonded to my carbon. All right, my oxygen gets its hydrogen from that acidic workup step. So not this one, this one. Okay, and this is this tricky way where they give you kind of this simple chemical equation here. They just tell you what's the product, but they're really making sure that you understand the mechanism of these reactions, right? That you know that our nucleophilic hydrogen here attacked that electrophilic carbonyl carbon. Cool. All right, so where we ended last time and where we're going to pick up this time was what we called our Grignard reactions. All right, this is the lab that we'll be doing today as well. Okay, so just to remind us, where we stopped was in sort of forming our products here. So I'm going to give you an aldehyde or ketone and a Grignard reagent, and you're going to give me the product of this reaction. All right, as a reminder, the whole special bit about these Grignard reactions is that you're creating a new carbon-carbon bond. Means your product's going to be all big and ugly compared to your reactants that you started out with, so you're going to make sure to count carbons at the end. Make sure you got everything correct. All right, let's remember the whole special bit about our Grignards. Carbon, we don't really think of as a very electronegative element because we're always comparing it to all the other nonmetals. But in this bond with magnesium, a metal, it is way more electronegative. So it's pulling all that electron density onto itself. So our Grignards are these carbon nucleophiles, right? And our aldehyde and ketone, as we said, that electrophilic carbonyl carbon. All right, so this is going to be our new bond that's formed between our nucleophilic carbon and our electrophilic carbon. All right, so what I'm going to do is I'm going to start, let's just redraw our electrophile here, these three carbons. Okay, again, counting carbons being really important, so I'm just going to kind of bookkeep here with color coding them. And I get to the end here, this is my electrophilic carbon. So now I'm going to draw my new bond that's created in this reaction, and what must live on the other side must be that nucleophilic carbon. All right, so then I'm going to sketch in my nucleophile had a total of these 4 carbons here. All right, this kind of isopropyl little fork. 1, 2, 3. All right, 1, 2, 3, 4. 1, 2, 3, 4. All right, so I've created my new carbon-carbon bond, but something's missing. I'm not done yet. First of all, what's the name of the chapter? Alcohols, right? So pretty good indication that I should be talking about an alcohol here at some point when I'm studying this reaction. So what I'm missing here is my carbonyl oxygen. That didn't go away in our reaction. We did look at our mechanism. You can convince yourself of this by looking at what we did last class. All right, but just to move quickly here, we didn't lose this oxygen. It just went from being a carbon-oxygen double bond to a carbon-oxygen single bond. All right, so we've created this alcohol by joining these two fragments here, creating this new carbon-carbon bond. Okay, so that's the direction that we went last class period. All right, now we're going to try to go the other direction. I'm going to give you this alcohol here, and you're going to tell me, well, I guess we don't want to do the exact same thing, huh? You're going to tell me what aldehyde or ketone we had to have started with, and what Grignard we would use in order to create this specific product. And I will tell you, there's actually two ways to do it. So try to come up with one. If you get it, try to come up with the other. All right, we'll discuss them both here. Wait, do you have an extra carbon? I think you got an extra carbon here. Just one, but yeah. Substitution. Do you like, or like, you know, get the substitution enhancement? Do you revisit the substitution or
No, I like very briefly revisited certain
Okay.
of it.
I definitely never like brought back that whole like table and categories thing or anything
I think
like
it's bring
that.
it back up again.
No, no.
Yeah.
Let's do something different.
I kind of, I've always like done this to substitution and kind of like quieted it, you know, tables where it would matter.
Yeah.
But I feel like I should be bringing it back up again.
It's like a reminder, not, I don't really spend time on it.
Okay. Slip it on an exam randomly or something.
No, I don't,
Okay.
we
Yeah.
do that, but homework questions or like in class questions, yeah.
Yeah, okay. Cool. So like when I look at this alcohol and I'm trying to think about what reactants I would use to form this alcohol, there's really only one thing I know for sure looking at this molecule, which is that this carbon right here must have been my carbonyl carbon, right? The one that has the oxygen bonded to it had to have been the one with that carbon to oxygen double bond. However, these reactions form new carbon-carbon bonds. So is this one over here my new bond, or is it instead my new bond on the other side? Well, again, that's why there are two different ways that we could use to form this specific alcohol, right? This could be my new bond over here, or this could be my new bond over here, all right? So if this is my new bond over here, that means that this must have been my nucleophilic carbon, so that these are all my, in this case, aldehyde fragment, and these are my two Grignard fragment, all right? So in this case here, my Grignard would be those two carbons. And my aldehyde would be all the other ones. Whoops. Be lazy and copy and paste here. Okay, so again, when we're looking at this alcohol product, what we know for sure is that the carbon bonded to the oxygen, that must have been my carbonyl carbon in my reactant. So if this is my new carbon bond over here, my Grignard fragment are those 2 carbons, my aldehyde fragment are the other half of that molecule. Okay, so then take a second, if you haven't already, using that same logic, give me my reactants that we would use to form this alcohol product here, right? Where now my new carbon-carbon bond is over here on this side. Okay, so if that's my new carbon-carbon bond, that means the one on the other side must have been my Grignard, right? Must have been my nucleophilic carbon. And my electrophile in that reaction, my aldehyde, would be that other fragment, those other 3 carbons. All right, so Grignards, bottom line. Given an aldehyde or ketone and a Grignard reagent, you should be able to tell me what that alcohol product is. And if I give you an alcohol, you should be able to tell me how to make it here using this Grignard reaction. Okay, I will say we said there are these 2 ways that you could do it. It turns out for Grignards, there's really not a preference of one being better than the other. There's going to be plenty of reactions where we'd be like, oh, do it this way and not this way. Grignards are like just remarkably flexible in that respect. Either of these 2 would be like perfectly equivalent ways to create that specific alcohol. Okay, so now we're going to go into our next category of reactions for this particular chapter. Substitution of alcohols. All right, I'm going to leave some room for some notes up here. And the first thing we're going to do is like kind of revisit when we were talking about substitution in the first place, which was not with alcohols. It was with that first functional group that we talked about, substitution with last semester, substitution of alkyl halides. All right, so a reminder, we took this alkyl halide and we said that we could substitute that halogen pretty readily for some nucleophile. So I'm just going to use our generic Nu nucleophile here. All right, so what's going to be playing the role of the nucleophile, the alkyl halide or the nucleophile? The nucleophile, awesome. Okay, so if the alkyl halide is my electrophile, specifically where is that electrophilic site in my alkyl halide? The carbon, right? So this carbon here, because of this polar bond, bromine's pulling all that electron density away from that carbon atom, right? Lack of electron density, whoops, positive charge, okay? And then importantly, it can accept this pair of electrons from the nucleophile because that halogen is playing the role of what? The leaving group. So we kick off that halogen, in this case that bromide ion, and we get this substitution where we've replaced that halogen with whatever our nucleophile is. okay? But we're not talking about alkyl halides anymore. We're talking about alcohols. So now let's try to play the same game here. Where instead of taking an alkyl halide, I'm going to take an alcohol. I'm going to take some nucleophile. All right. And let's think about trying to play the same game here. Well, so first of all, is this a polar bond? Yeah. Oxygen's the second most electronegative element. So if carbon-bromine bond's polar bond, this is definitely a polar bond, right? Not only that, but is the oxygen pulling electron density onto itself, leaving this carbon atom with this partial positive charge? Yes, because my oxygen is more electronegative. It's pulling that electron density. Okay, great. So then we're going to play the same game here. Nucleophiles, a lot of electron density, attacking electrophiles. Not a lot of electron density. We get our substitution product here. All right, but it turns out this isn't going to work. You do not get this substitution product here. Okay, so why not? Awesome. Okay, because what's the other part that we had to do? We had to kick off that leaving group. In this case, what we kicked off would be a hydroxide ion. And hydroxide ions are probably need a negative charge on there. Hydroxide ions differing from my bromide ions. Bromide here is a great leaving group, right? Good leaving group. Hydroxide, a bad leaving group. Which is why we don't just have this simple nucleophilic substitution reaction, all right? But I said bromide's a good leaving group, hydroxide's a bad leaving group. How am I supposed to know that, all right? What is it about hydroxide that makes it a bad leaving group? Cool, all right, yeah, reactive, base, all good things, all right? Yes, so our good leaving group, a bromide ion, yes, it has that negative charge, but it's a terrible base. Right? It's the conjugate base of that strong acid, hydrobromic acid. So what makes a good leaving group is that it's a weak base. What makes a bad leaving group? We have a strong base. Okay? So, substitution of alcohols. What we're going to find here is that our alcohols are kind of hard to substitute. Because that hydroxyl group is a bad leaving group. So if we really want to swap out that hydroxyl group for some other functional group, our strategy that we're going to have is to convert that hydroxyl group into a better leaving group first. All right? So all of these substitution of alcohols, what we're going to see is we're first going to convert the OH into a better leaving group. And we're going to see a few different strategies for doing this. Okay? Cool. So the first one is to just go back to what we know works, those alkyl halides, those halogen groups, right? So our first step, or our first strategy of substituting our alcohols is going to be to convert our alcohols into alkyl halides. Okay. Similarly to when we were talking about oxidation reduction reactions, we took alcohols and we broke them into these categories of primary, secondary, tertiary, right? They reacted differently depending on their degree of substitution. We're going to see the same thing here for our conversions of alcohols to alkyl halides. We're going to again need to talk about them in those different categories. All right, so first we're actually going to jump to the end here. We're going to do our tertiary alcohols. All right, and these are actually the easiest to do. By easiest, I mean like literally takes, mix two things together, shake it up, in 10 minutes you have 100% yield kind of deal. Super cheap reagents. If we just use hydrochloric acid or hydrobromic acid, we will substitute off that hydroxyl group for those respective halogens. All right, so hydrochloric acid, we would create an alkyl chloride. Hydrobromic acid, we would create an alkyl bromide. Okay. For these reactions here, we're going to look at our reaction mechanism. And what we're going to see in this reaction mechanism is this strategy that we kind of use often, or we're going to see a few times here, to replace that hydroxyl group by making it a better leaving group by adding acid. Okay, so we're going to take this as well as we'll do hydrochloric acid. All right, and let's see if we can't predict what's going to happen here. Right, we want to see, look at these two molecules and decide which one's going to be our nucleophile and which one's going to be our electrophile. All right, so everybody take a second and see if you can't figure out which one's your nucleophile, which one's your electrophile in this reaction. All right, in this first step in our mechanism here. All right, first of all, nothing's got that net negative charge. Like nothing jumps out to me as like an obvious nucleophile here. Alcohols can actually sometimes play the role of both, but hydrochloric acid being an acid means it's going to play the role of what? Yeah, so the electrophile with its leaving group, right? So in our acids, where is our electrophilic site? The hydrogen, right? That acidic hydrogen here is going to be our electrophile. And so if that's the case, and our alcohol's the nucleophile, where's the nucleophilic site in that alcohol? The oxygen, and how do I know it's the oxygen? Because of the lone pair, right? Because that pair of electrons. Okay, cool. So we got our nucleophile, we got our electrophile. What do nucleophiles do to electrophiles? Attack. All right, and we'll kick off that chloride ion as our leaving group. Okay, so by adding that strong acid, what we've done is we've protonated our alcohol, added a proton to that oxygen. And since I've converted that lone pair into a bond, what am I going to need to do to finish off this structure? That positive charge on that oxygen. Okay, now this next step here is actually just an intramolecular rearrangement here, or rather we're only going to be looking at this intermediate. Because this is a tertiary carbon here, it can form a carbocation by kicking off that water. All right, so basically, before we move on here, let's just note, because we're going to see this strategy again, we've converted this terrible leaving group, this hydroxyl group, into a good leaving group by protonating it. Now when it leaves, it won't leave as that strong base hydroxide, it leaves as that neutral water molecule, right? A nice weak base. Okay, so now you're going to take a second and finish off this reaction for me. Again, we've formed this alkyl chloride product. All right, so in order to go from here to here, I'm going to need a bond formation arrow. I'm going to start at that lone pair on that chloride ion and attack that carbocation. All right, and that's my bond formation, taking me to my alkyl halide product here. Okay, now importantly, this worked because we had that tertiary alcohol, meaning it was bonded to a tertiary carbon, and tertiary carbons can form those more stable carbocations. All right, it turns out if we instead have a primary or secondary carbon, there's a different method that we want to use. Truthfully, you can try to force this method here with like a huge concentration of acid and a lot of heat, but you typically get like pretty crappy yields. So it's just not the preferred method, trying to use those hydrochloric and hydrobromic acids. All right. So instead, for our primary alcohols, we're going to have a better, more efficient way to do it here. Okay, so same idea. We're again converting our primary alcohol into alkyl halides. We can turn it into an alkyl chloride or an alkyl bromide. All right. But again, we're going to have these different sort of more designer reagents here. Nothing quite as simple as hydrochloric or hydrobromic acid. We're going to spend some money here, and we're going to buy what's called thianyl chloride, so SOCl2. Or phosphorus tribromide, PBr3. These are our preferred method for converting primary alcohols, as well as secondary alcohols, as we'll see in a second, into our alkyl halides. All right, just much more efficient than trying to use that hydrobromic or hydrochloric acid. All right, we're going to see the same thing for our secondary alcohols. But with secondary alcohols, we have a little bit of a twist that we can throw on this. Primary alcohols, just by definition, that carbon has to be bonded to two hydrogens, meaning it can't possibly be a stereocenter. All right. Our secondary alcohols, though, we can have a stereospecific alcohol. So looking specifically at the R enantiomer of 2-butanol. All right, so we're going to use our same two reagents here, thianyl chloride and phosphorus tribromide. But now we're going to be using it on this stereospecific secondary alcohol. And so what we're going to see with our secondary alcohols is we have to worry about what we call stereospecificity. If I start out with a stereospecific alcohol, I'm going to get a stereospecific product. Okay? Now, this is not a mechanism that I would expect you to know, although it is well known. We could look it up in the textbook. Suffice it to say that sulfur kind of globs onto this oxygen to make it a better leaving group. What we do need to know about these reactions, though, in terms of their mechanism, is that they are SN2 mechanisms. All right, digging back from last semester here, both of these would be considered these binary substitution mechanisms. And what that meant in terms of our stereospecificity, if we remember back to last semester, we get what we call a stereochemical inversion. Which means if I started out with this R enantiomer of my alcohol, when that chlorine did its nucleophilic attacking, it attacked from the back side, giving me the S enantiomer of my alkyl halide. All right, so Our secondary alcohols, because they can be stereospecific, we got to worry about our stereospecificity of our reaction. And in this case here, they are SN2 reactions, meaning we have this stereochemical inversion. And that's the same regardless of whether I did my thionyl chloride or my phosphorus tribromide. Both of these would give me this stereochemical inversion. Okay? So basically, we got to keep track of our stereochemistry using these dashed and wedged bonds. I know, exciting. Okay. So we talked about tertiary alcohols. We said we use these different reagents here, just hydrochloric acid, hydrobromic acid. Let's kind of revisit this idea of tertiary alcohols and their substitution, thinking now about our stereospecificity. All right, so we're going to say tertiary, and we want to think about our stereospecificity. Because I gave you this like perfectly symmetric tertiary alcohol when we first did it, but we don't have to, right? We could have a stereocenter with a tertiary alcohol. So let's look at a stereospecific tertiary alcohol and try to think about how this is going to go down. All right, I'm just going to pick one of our two reagents since they're equivalent. You know, my favorite is bromine, so we're going to go with HBr. Okay, and I'm not going to do the full mechanism here, but let's just remember our intermediate, famous intermediate we've seen over and over again. What do we call it? What's this guy? Carbocation intermediate, right? So, world famous carbocation intermediate here. Our carbocation is going to form on that carbon that had my hydroxyl group after it gets kicked off. But what do we know about the hybridization of a carbocation carbon? sp2, which means it is trigonal planar. Right? So now all these three bonds are in the same plane. So it goes from being a tetrahedral to now being this completely flat trigonal planar here, meaning that my nucleophile can attack from either side equally as effective. Right? So 50% of the time the nucleophile is going to attack from the top, 50% of the time the nucleophile is going to attack from the bottom. So even if we have a stereospecific alcohol here, we're going to get a mixture of our R and our S enantiomer on the other side. What do we call that 50-50 mixture of the two enantiomers? A racemic mixture. Awesome. So our stereospecificity here, we basically lose our stereospecificity. In the fact that we get a racemic mixture. All right, to be clear, your products are still stereospecific. It's just that you get that 50-50 mixture of both. All right, and so we could draw both of them down with both of our dashes and wedges, or we said we can represent our racemic mixtures simply with our straight line bonds. Okay, so even if we start out with a stereospecific tertiary alcohol, because of our mechanism, because it's not SN2, it's going through that carbocation intermediate, we're going to lose our stereochemistry or produce a racemic mixture in this reaction. Cool. So our whole goal was to substitute that hydroxyl group. All right, what we're going to do is first turn it into a better leaving group. But then the whole point is we want to be able to swap it out for anything, right? So now we're going to follow this up. This is now actually where we're going to really do our substitution. All right, substitution of alcohols. And what we're going to use is that method of converting alcohols to an alkyl halide. Okay, so I'm going to take a primary alcohol here. I'm going to first convert it into a better leaving group by adding, in this case I'll do thionyl chloride. But then I want to substitute off that good leaving group for some nucleophile. All right, so let's use sodium methoxide here. All right, so to be clear, what we've just talked about is that that first step is going to replace that alcohol group with that chlorine. All right, I'm going to convert my alcohol into an alkyl halide using that thionyl chloride. Okay, but now I'm adding this sodium methoxide here. So first of all, what's the sodium doing for us? Nothing, right? Yeah, just a counter ion. So when I see something like this, I immediately get rid of the sodium and replace it with a negative charge because it is just playing the role of the counter ion. And this thing with its negative charge, I need to be able to recognize as a nucleophile, right? So what we're going to have is this backside attack. Going to come from the opposite side here, kick off that chlorine leaving group, leaving us with our substitution product. In this case, my functional group here. What is my functional group? Also, I miscounted carbons. What's my functional group? Sorry? Ether. The ether bunny. I got you. I told you. You'll never forget it. Okay. All right. So, yes, we've created this ether here because we had this nucleophilic substitution on that carbon. Okay. Cool. So now we're going to do the same thing, but we're going to look at a stereospecific secondary alcohol. Bless you. And we're going to play the same game. We're going to convert it into an alkyl halide. In this case, we're going to use our phosphorus tribromide just to mix it up. We're going to add in another nucleophile here. Cool. No, I just think about stereochemistry that's going to happen there. You got the first flip down, but what about this second step? SN1 or SN2? All right, so everybody, we sort of got our first step down. We know the name of the game, converting our alcohols into alkyl halides. As we said, there's going to be this stereochemical inversion. So I'm going to draw my 5 carbons here that are all in the same plane. All right, but then this carbon right here, my second carbon, going to be on a dashed or a wedged bond, my new functional group. Dash bond, right? We had that stereochemical inversion. What about this one here? I put a second stereo center in this molecule. Am I also going to convert this from a dash to, or from a wedge to a dash bond? No, because there was no reaction at that carbon, right? That carbon wasn't involved in this reaction at all, so it's just staying exactly as it was. Okay, and we said that there was this stereochemical inversion because this was an SN2 reaction, right? That backside attack of my nucleophile. Well, now I'm adding in this sodium hydrogen sulfide here. That sulfur has that negative charge because I know the sodium's not doing anything. So again, I'm just adding in some nucleophile. When that nucleophile attacks, what's going to happen to that stereocenter? It's going to invert back, yeah, because this is also an SN2 mechanism here, right? The sulfur has to attack from the opposite side of where that halogen is in order to kick that halogen off. So we have yet another SN2 step here, which means, yes, we flip our stereochemistry, and then we're going to flip it back again when we do our second nucleophilic attack. Cool. Okay, so now we're going to go to our last example here, our tertiary alcohol. I'm just going to grab this same one. Again, now we're trying to substitute out that hydroxyl group for some nucleophile. So we're going to first convert it into a halogen. All right, using that method. Remember, we have a different set of reagents we use for our tertiary alcohols. We're going to use hydrochloric or hydrobromic acid instead. And then we're going to do some nucleophile here. I'm going to use this as an example to remind us of that azide ion nucleophile. All right, so importantly in that first step, we're going to convert our alcohol into an alkyl halide. And what's going to happen to my dashed and wedge bonds? What's going to happen to my stereochemistry? I'm going to lose it, right? I'm going to get that racemic mixture, which we're just going to represent with our straight line bonds here. Which means that when I follow it up with that second step, am I going to get a stereospecific product? No, I don't start out with a stereospecific set of reactants here. Not only that, but if you remember, our substitution mechanisms for tertiary alkyl halides were SN1 anyway. So even if we did start out with the stereospecific alkyl halide, we would still lose our stereochemistry when we do our substitution. All right. Just to kind of remind us real quick, This thing here, again, sodium's not doing anything for us. This is our nucleophile. This is what we call an azide ion. If we do our Lewis structure for our azide ion, we would see that we have our nitrogens all bonded in a row here. All right. My terminal nitrogens, given that they only have 2 bonds, how would I complete their octet? How many lone pairs? 2, meaning that they have what charge? Negative charge. And what about my one in the middle with its 4 bonds and no lone pairs? Positive, which is how we have that net charge of -1 in this molecule. All right, good nucleophiles. Okay, that's going to substitute off that halogen. We'll draw out the full. You could just abbreviate it N3. I'm going to, like we would on our homework, put in my Lewis structure here. Just kind of ugly. Make a little bit more space for myself. Cool. All right, so importantly with our tertiary alcohols, again, we're going to lose that stereospecificity. Even if we start out with the stereospecific tertiary alcohol, because of that carbocation intermediate, we're going to get a racemic mixture when we form our alkyl halide. And even if we did in substitution of alkyl halides, there's also going to proceed through that carbocation intermediate. So bottom line is we get a racemic mixture of our products. Okay, so we have this one method for substituting alcohols by converting them into alkyl halides. There's another method, another strategy that we're going to talk about. And that is to, again, the whole name of the game being we have to turn that hydroxyl group into a better leaving group. So this is just another better leaving group that we can do. We're going to turn our alcohol into what's called a tosylate group. Okay. We're going to talk about tosyl chloride. And truthfully, you will see this abbreviated most often, but just to kind of draw it out and look at our Lewis structure here. All right, we got this sulfur double bonded to some oxygens with a chlorine. And then it's got this whole pi bond system, this whole benzene ring on the back end here. All right, it turns out that it's not actually benzene, it's toluene. There's a methyl group on there, which I don't know why. Do you? I mean, it's just safer to work with or something like that? I mean, it should work just as fine without it, right? Yeah, okay. Anyways, a tosyl group has this methyl group on there as well, okay? So it...
That's why it's called that. That's the word,
But do they use it, like, do they just have, like that should work just as well? Okay.
Yeah.
This is just the go-to? Okay. I imagine it's either easier to produce or safer to work with or something like that. Yeah, okay. Anyways, so it turns out that if we take an alcohol and we add in that tosyl chloride, okay, again, not too crazy of a mechanism, not one I'm going to expect you to know, but suffice it to say that our oxygen is going to be playing the role of the nucleophile in this step here. This carbon is not involved in this reaction at all. And what happens is that tosyl group just kind of globs on to that oxygen. And again, I'm going to draw out the full Lewis structure here, and then I'll show you how we can abbreviate it. What's up? So I'm going to show you how we abbreviate it. what I really want is that you can sort of recognize the structure, because on the ACS exam, if you remember from last semester, it showed up as both the abbreviation and the actual Lewis structure. So being able to recognize this as what I'm going to sort of spoiler alert, a good leaving group is going to be really important. Okay, and we could make our lives a lot easier by just simplifying this rather than drawing out that full Lewis structure as just OTS. All right, so this is just represented by this in our abbreviation. Okay? And the whole shtick here is that this that we've just created, we've now replaced that hydroxyl group that was a crap leaving group with a fantastic leaving group. All right, you can convince yourself that when this thing gets kicked off and there's that negative charge on that oxygen, it's just about as maximally resonance stabilized as it could possibly be. Not only by those double bonded oxygens, but also by that benzene ring. So just a nice stable leaving group that this thing gets kicked off as. Okay? Cool, so then let's imagine we talked about this would be a primary alcohol. Let's play the same game here, but with a secondary alcohol. And again, with secondary alcohols, we have that whole stereospecificity business. Okay, so again, I'm going to start out with a stereospecific secondary alcohol. Add in that tosyl chloride. I'm just going to use my abbreviation from here on out. Okay, but if oxygen's going to be my nucleophile in this reaction here, right, what is my stereochemistry of my product going to be? Am I going to see that same stereochemical inversion? Is this carbon involved? No, it's not getting attacked. It's not my electrophile. The oxygen's the one doing the attacking. So if I add this tosyl chloride, if I use this tosyl chloride method, we're going to see that we preserve our stereochemistry. All right, I start out with my R enantiomer of my alcohol. I get my R tosyl group thing on there. I don't know how to name that thing, but yeah. Okay, so let's then start pairing these up, because again, we're trying to substitute, we're trying to kick off that good leaving group for some other nucleophile. So let's start taking these reactions and pairing them up. All right, we're just going to jump right to the punchline here. I guess we've been doing that same R enantiomer. We'll switch it up. So now we're going to again make that hydroxyl group into a better leaving group, but using this other method here of our tosyl chloride. And then adding in some nucleophile. Oh, I don't want to use that one for reasons I don't want to go into. Exactly what I was saying. Okay. All right, for the sake of time, we're just going to power through this one here. First step, convert that into a better leaving group, making that tosylate ion, or not ion, tosylate group on there. And again, that first step now preserves our stereochemistry. So now what's going to happen when I do step 2 here to my stereochemistry? Is it also going to be preserved? No, why not? Because of the backside attack, because of our substitution mechanism. These are SN2. There was a reason why we had to flip it back in our previous example. All right, we preserve stereochemistry in that first step, but we're going to get a stereochemical inversion when we do our substitution. All right, in this case here, what am I adding on to this carbon? What's my new bond going to be? Carbon what? Sulfur, because when we get rid of this, replace it with our negative charge. That's my nucleophile here. Okay. What if we did a last one that we're going to sort of make sure to cover here? Let's instead take a stereospecific tertiary alcohol. All right, that first step there, am I going to lose my stereochemistry? Is this carbon involved in that first step? No. So I will get this stereospecific tosyl group on there, tosylate group on there. But what do we know about substitution of our tertiary carbons? This, to be clear, is just a really good leaving group. It's equivalent to if it was like a tertiary alkyl halide, right? Just a bomb leaving group on there. So our substitution of tertiary carbons, is that SN2 or SN1? Those are SN1, proceeding through those carbocation intermediates. So even though I preserve my stereochemistry at that first step, I'm going to eventually lose it when I get to my next step here, when I do my actual nucleophilic substitution. Oops. Cool. All right. Sort of just did a rewind as to what we've covered thus far with regard to our alcohols, right? We have our hydration of our alkene reactions, kind of a review from first semester. We then introduced these oxidation reduction reactions. That's kind of a messy one. Let's just go to this one. Oxidation reduction reactions, as well as we can form our alcohols using these Grignards, what we're going to be doing today in lab, creating those new carbon-carbon bonds. All right, and then what we did today was introduce a new category of reactions, our substitution of our alcohols. We got 2 ways to do it. Both of them are, the logic is to convert them into better leaving groups. We can either convert them into alkyl halides, or we got this fancy little tosylate group that we can add. Again, just turning that hydroxyl group into a better leaving group so that we can substitute it off for some nucleophile. All right, cool. We will pick up and close out our discussion of alcohols next class period.